Oh, yeah, I think we are ready. So if you have any questions, then it's a good moment to ask them. Be brave, because I like your questions. In my opinion, the whole education is just about questions. It's a question, or it was not? Yeah.
Professor?
Yeah.
Professor, I wish to ask if it's possible that at the end of the lecture we are able to have an access to the material. Possible?
What do you like to have? Sorry, what would you like to have?
Professor, I was asking if it would be possible. We would like to have the material of the lecture of today. That is stochastic calculus. We would love
Yeah,
to
I
have the
post
material at the end of the
videos.
lectures.
I post videos on YouTube with some delay, but I post them eventually. Yes. So if you're about video lectures or what materials? What material do you like?
No, just the material, Professor. Just the material. The
Video recordings of what?
to read
What do you mean by?
is much more.
I don't understand.
I was talking of the material that's to study later on, to read on them.
Sorry, I don't understand. Would you like video lectures, PDFs with my handwriting, or do
PDF,
you mean
PDF,
external
PDF.
PDF? Okay, yeah. But I think I dropped them immediately in the
PDF.
chat, so they are all in the chat. Join it if you like. Okay, so let's continue. So last time we have discussed stochastic integral, and what we have intuition behind stochastic integral. Yeah, we have intuition that it's like profit. Yeah, so using this simple intuition, we can calculate stochastic integrals that are stepwise constant. Yeah, we can, if AU is something like this, so it's a process, so we have discrete transactions. So this intuition is sufficient to calculate a stochastic integral for continuous for countable number of jumps case. Okay, we have almost honest definition. That it's not a honest definition, because in a honest definition we should take intervals of probably different lengths, but anyway we have subdivided our time interval into n sub intervals. We have n sub intervals, and we have like defined that our integral is a limit in L2 of In, where In is the approximation that is understood as a piecewise constant case. So basically, now let's go to properties of stochastic integral. What are the properties of stochastic integral? We are interested in the properties of stochastic integral. So first, some assumption. I will not prove these properties. So basically, they are almost all they are expected, but intuitively they are more or less clear, but I will not prove them because we have not enough time to make a honest definition. So, okay. So I will assume that that WT is a winner process with respect to some filtration FT. AT is adapted to the same filtration. I will also assume that AT is continuous with probability 1. I will also assume that what else do I need? I need some technical stuff like integral of expected value AU squared du is like the infinity, how it exists. I think that's all. Continuous, adapted, small second moment, that imply first moments. Okay, so this will be my assumption. I will not check them, that just for some rigorous statements. And now properties. So first property are just like ordinary integral. You may add, you may change the order of integration, some boring properties, properties that, I don't know, integral from 0 to t AU plus BU dWu is equal, you won't believe me, AU dWu plus BU dWu. What else? Integral from 0 to S AU dWu plus integral from S to T AU dWu is integral from 0 to T AU dWu. What else? Integral from A to B AU dW. dWu is something minus integral if I interchange limits and so on. So you may take out constant lambda times AU d, but that's boring. That's all non-interesting properties. They are true, you may use them, but nothing is new here. Let's move on to something more interesting. So something more interesting. Fun. First idea is very simple. We like invest in a winner process, in a Brownian motion. Essentially, we cannot make profits because we cannot predict the future increment. Future increment is independent of past information. So basically, that means intuitively for us that our integral from 0 to t AU dWu is a martingale, because we are investing. AU represents some trading strategy, and dW, so this is quantity once again. This is price of an asset, and our profit is a martingale. We can increase our profit, we can encounter some losses, but it's a martingale. So from this property, it follows that expected value of IT given Fs is just Is, S is less than T, or we have a necessary condition for a process to be a martingale, that expected value of IT is constant. But in this case, it's an integral from 0 to 0 AU dWu, and it's 0. So it's a martingale. Any stochastic integral is a martingale. I'm not speaking about some extreme cases where my assumptions are violated, but if my assumptions are satisfied, then it's a martingale, and expected value of any stochastic integral is 0. Okay, so that's it's very easy to calculate expected value of stochastic integral. Let's go on. So it's the first interesting property. Okay, please answer. I cannot, I'd like to be interactive. Everything is okay?
Yeah, it's clear.
Yes.
Yeah, thank you very much. Please.
Yes, clear.
Yeah, thank you. Okay. We have, third property is called isometry. Basically, it's a consequence of a result we have proven last week. Last week we have a result that we have a honest proof of that result, that if you consider the sum of WIT over n minus WI minus 1 t over n squared, sum from I to n, when n tends to infinity, this random sum tends to what? Who remembers? It was a very interesting. It tends to
T divided by m.
t, just t, because it's a sum. We have calculated expected value. It was t. We have calculated variance, and variance tends to 0. Expected value is constant t, and the result follows. Okay, so this property we have proven, and it follows because integral is a sum. So basically, the proof is based on this fact. So basically, that's a consequence that squared increment of Brownian motion roughly tends to delta t. And expected value of an integral from 0 to t au dwu squared, because integral is the limit. So basically it is integral from 0 to t, expected value of au squared du. Okay?
Okay.
So, or we may state it differently, variance of a stochastic integral, because expected value of stochastic integral is 0. So basically, variance is expected value of au du. So this property allows us to calculate variance of a stochastic integral. We may calculate expected value of stochastic integral, y du, not dwu. Ruslan, that is the idea. We have proven that roughly, so look at this limit we have proven last week. If I write it differently, what does it say? It says sum of delta w w, let's say I squared, is the sum of delta t. Yeah, basically I may write it like this. So sum of delta u squared tends to sum of delta t, and basically you can see a reincarnation of this limit here. It's not a honest proof, I understand, but the idea, what is the reason, what is the deep reason behind this result? So the deep reason behind, so if you like honest proof, I think honest proof is, you may find it in Baldi, I'm sure. I'm not sure whether Zastavnyak has the full proof. I think yes, Zastavnyak, yes. But I'm not sure. But Baldi, yes, for sure. And Zastavnyak, I'm not sure. So if you are interested in a proof, so go look into the books. If you are interested in some soft argument, we have a honest proof of this limit. You may write it like this. So when you sum squared deltas of winner process, you obtain t, or the sum of delta t's. So basically, if you add some multiplier inside the sum, basically the result doesn't change. Okay, so it is isometry. It may be generalized to two processes. So it is isometry. So it will be force. It is isometry for two processes. So if I like to calculate covariance of AU dWu and second integral some BU dWu, I may just calculate expected value of the product. And here I change the integral to ordinary Riemann integral. Okay, what else do we have as properties? The fifth property is not a property of a stochastic integral, but it's a good point, it's a good moment to stay it here. So basically, it's an old property, but just for comparison. It's not a property of stochastic integral, but if you are calculating expected value of ordinary integral, then you can just, for the process we have stated, you can just change the order of integration. So we have some assumptions. Could you please return to the previous page? Yes, I can. Okay, let's continue. What else do we need? I think we can calculate expected value, variance of stochastic integral. What else? And basically, that's all. The last property we need, it's Ito's lemma. Ito's lemma, but because of its importance, we will state a path. It's obviously a property of stochastic integral, but let's state a path. First, I would like first thing I would like to mention when I speak about Ito's lemma is that there are many shorthand notations agreements in mathematics. So there are some shorthand notations agreement in mathematics. So you know some of them, not so a perfect example of a shorthand notation, when you write something like x squared is small o of x. What do you really mean when you write this? This is just a notation. Yeah, what do you really mean when you write that x squared is a small o of x?
What's your function?
Sorry? What's the exact meaning?
It is not significant.
What do I mean not significant?
Could it be that it's like a function, blah, blah, blah?
Okay, it seems no one knows what does this mean.
No, x squared is something relatively small of x.
Yeah.
It is the part that we do not consider.
Yeah, it means that the limit of x squared divided by x, so intuitively it means that x squared is comparatively small to x when x is 0, when x tends to 0. Yeah. So if I say x cube is a small o of x, that means x cubed divided by x when x tends to 0 is 0. Okay. Yeah.
Yes.
Yeah. Do you remember? You have used this notation in calculus. This is like first year undergraduate notation. Yeah. Do you remember it? Who has
Not
used
for
it?
sure.
Is it from like Taylor approximation or something like that?
Yeah. Who has used small o notation? Anyone? Because it's I'm a little bit surprised.
Yes.
We
Yes.
have used it, yes, in September 1st course undergrad.
Okay. Okay. Yeah. Thank you very much. Okay, but you should perfectly understand that it's only a notation. Yeah. It's not a honest equality. Yeah. It's a notation that's very useful. Yeah. But it's not a honest equality. Yeah, because if it is a honest equality, then something strange is happening. Yeah, x squared is o small of x cube is o small of x, but it doesn't follow that x squared and x cube is the same function. Yeah. So it's a useful notation, which is very widely used in calculus course. You can calculate easily many limits with this notation, but it's only a notation. Yeah, we cannot say so if this. So we cannot say that O small is equal to O small. Yeah. So x squared is. So we really mean something more complex than a simple equality when we write this special symbol. Okay. So my main idea that there are some shorthand notations in mathematics, and if we are used to these notations, then they are useful, but they are not not strict equality. Yeah. Now I go back. So this is my digression from my main path, and now I go back to Ito's lemma. To represent Ito's lemma without shorthand notation, it would be a very big, messy theorem. But we will introduce shorthand notation, and with shorthand notation, Ito's lemma is very pretty. Okay, so we will introduce shorthand notation, and using shorthand notation, we will introduce Ito's lemma. Okay, in our case, once again, this is just a shorthand notation. This is just shorthand notation. We will write dAt equals to dxt equals to at dt plus bt dwt, and this will really mean. So this is just a notation, and this will really mean that xt is x0 plus Riemann integral au du plus stochastic integral bu dwu. This is meaning. Okay, we will introduce this shorthand notation. Why it's a shorthand notation? Dxt has no meaning. Dwt has no meaning. They do not exist. You cannot just say dxt is a random variable, I will take expected value of it, or dxt is a random process, I would like to ask whether it's adapted to some filtration or not adapted. So dxt has no meaning. There are no such thing as dxt. There are no such thing as dwt. But we will use this, we will just save ink. Instead of writing big formula with integrals, we will just sometimes write short formula without integrals. But really, this is just notation, and that is the meaning. Okay, so it's a so the question, what is the value of dxt? That's a nonsense. Dxt has no meaning by itself. Can you go up to the previous notation? Oof, previous notation, previous. Yeah, it was just a recall from calculus. So if you do not know small o notation, I will not explain it. So that I will not use it. So my main idea was that there are shorthand notations in mathematics. They are not honest equalities. Small o of x is not a function. So you cannot say that, oh, I have small o of x and this is function. I will draw it, the plot of it. You cannot draw this function because o small of x is not a honest function. It's more like a class of a function.
Okay, that's clear, Professor. That's clear. It's clear now. Thank you.
Okay,
Thank
now
you.
let's go back.
Boris Borisovich,
Yeah.
could you please explain what corresponds to what in notation to the meaning? AT dt is for the integral of AU du, right?
Yeah.
WBT is the integral, and xt minus x0 is dxt. Yes?
No.
Not is, but stands for as a notation, right?
No.
And
The whole as a whole. No. dxt has no meaning. No, the whole as a whole. I write that, I mean that.
okay.
So that's just, I write this, I have that. That's all. So I cannot write like dxt corresponds to xt minus x0. No. So just this is a notation for that. And let's check on some examples. So if I write dxt is like in a Black-Scholes model, let's consider in Black-Scholes model, we often write dst is just mu st dt plus sigma st dwt. So this is Black-Scholes model for share price. And this is a shorthand notation. This has no meaning by itself. So what do we really mean? We mean that st is just s0 plus integral from 0 to t mu su du plus integral from 0 to t sigma su dwu. So you write the whole equation, it has a full meaning. Okay?
Yeah, okay.
So this is a shorthand notation. This is full form. Here we can have a honest meaning of each term. Each term is a limit of a random sequence in L2. So basically we have a meaning of each term, and so this is a honest mathematical object. We can ask ST or ST, we can calculate expected value, variance, I don't know, probability that ST is greater than 5, but it's a stupid question to ask what is the probability that dxt is greater than 5. So we have no dxt as an object, yeah, just a shorthand notation, okay? The notation is clear?
Okay.
Yes.
So it's just a notation, no meaning for each term, just the whole equality has a corresponding full form analysis. So once again, let's do one more exercise. So if I will go back from full notation to shorthand. Okay, if I have let's say xt is 5 plus integral from 0 to t twt squared dwt. What is, so this is full form. What is dxt? Shorthand notation.
U, W, U.
Oh, so, oops, sorry. It's my fault because I cannot use the same letters in limit and sorry, it's my fault. I need to have different letters, U and T. So inside integral and as a limit, they should be different. So once again, my question, what is dxt shorthand notation?
T, bt squared, dv.
Yeah, wt squared, dwt. Okay?
Yeah.
So
Yeah.
we write this, we mean that. Okay. So now definition and Ito's lemma, I think, definition. A process like process xt, that is x0 plus sum of two integrals. It happens that many processes, almost all continuous stochastic processes, can be represented in this form. So this is very rich form. A sum of two integrals is gives us a lot of possibilities. So this form xt du plus stochastic integral bu dwu. This process is called Ito's process. So there are some processes with jumps that
please.
cannot be represented in this form, but almost all stochastic processes with continuous path can be represented in this form as a sum of two integrals. So we will study this form. But there is a very interesting theory of stochastic process with jumps. That's very fun. You have jumping. Oh. Okay, let's move on. Let's finally state the Ito's lemma. Ito's lemma. That will be our first Ito's lemma. We will we will generalize it for two or more processes, but for the moment, let's write it for one process. Ito's lemma first. So if you have yt is a function of t and wt with, what do we need? We need f prime of t, f prime of w, f prime prime of ww continuous. We need also assumption that we have stated before, that we have a convergent expected value of Riemann integral. So then dyt equals to f prime with respect to t dt plus f prime with respect to w times dwt plus a very strange term that is not present in ordinary calculus. I will add it in a other color. 1/2 times f prime prime with respect to ww dwt squared, where wt squared is equal to dt. So let's apply Ito's lemma. Let's apply Ito's lemma and see what is the meaning, so why it's useful. Okay, let's apply Ito's lemma. Example 1. Let yt be equal to wt squared. Okay, let yt be equal to wt squared. So my function f of twt is just wt squared. So what is dyt? Dyt is f prime with respect to t, 0 times dt plus f prime with respect to w. What's it?
2wt.
2wt. If you take a derivative.
I said 2wt.
Ah, 2, yes, then you are right, because I've heard on only one. One was lost. Okay, 2wt. Yes, then you are right, sorry. But
Yeah, sure.
okay, dwt plus 1/2, this strange correction, times second derivative is
2.
2 times dwt squared, but this term is dt. Okay, so we have dyt equals to 2wt dwt plus dt. But we understand that that equation has no meaning by itself. dyt is not existent. We cannot say expected value of dyt, variance of dyt. It's crazy idea. So it's a shorthand notation. Just a shorthand notation. What is the full, honest meaning, full form? Yt is equal to what?
Y0.
Y0 squared. Oh, sorry, Y0 plus
Y0
integral from 0 to t,
to t
1 times du plus
Yeah.
integral from 0 to t, 2w times dwu, okay?
Okay.
Yeah.
Now, what is the yt? It's wt squared. What is y0? It's w0 squared. What is this integral? I can easily calculate it. So it will be t, 2 times integral from 0 to t, wu dwu. And finally, this is 0. And finally, I've got integral from wu dwu, that is wt squared minus t divided by 2. And this completely agrees with our result of last week. Yeah, last week we have calculated this integral stochastically, but we have used limits, L2 convergence, and that was fast using Ito's lemma. The result is the same, obviously. The result is the same, but it was obtained faster using Ito's lemma. Okay, do you remember that we have calculated this integral using limits?
Yes.
Yes.
Yeah.
So basically, we have an opportunity to simplify some expressions involving stochastic integrals using Ito's lemma without taking limits, thinking about convergence. So that's basically like chain rule for ordinary integration. Yeah, it's like analog of like chain rule. Okay, let's consider some more examples. Example 2. Let's consider integral from 0 to. So let's consider wt4. What is the dyt? Is 0 times dt plus, I will go a little bit faster this time, 4 times wt squared dwt plus correction term 1/2 times second derivative, it would be 12 times wt squared times dwt squared, and this is 4wt cubed dwt plus 6wt squared dt. This is my result. Okay, this is a formula that has no meaning by itself. I'd like to point out that this is meaningless expression. You cannot say variance, covariance of these two terms. They're not random variables. They're not random processes. They're not constants. So it's like a garbage, but it's a usable garbage. We can reconstruct from this nonsense formula, we can reconstruct full form that has meaning, where we can calculate variances, expected values, and so on. So what is the full form?
y0 plus integral from 0.
Yeah, wt power 4 equals to w0 power 4 plus integral from 0 to t.
6w squared.
Or 4w, it doesn't matter.
Yeah, because these are honest term. Yeah. So you can write here 4w squared du plus integral from 0 to t 6w squared du. Okay.
Okay.
So now it seems we have that's another idea that many stochastic processes are just sum of two integrals. So this is another proof that almost always we can just write some stochastic process as a sum of two integrals plus constant. So it's a very strange idea that many stochastic processes can be represented as a sum of two integrals. Okay, so let's use this equality. For example, let's calculate, let's add one more point. So the first point in this exercise was calculate dy, and let's calculate expected value of w power 4, because I think we will use properties of stochastic integral. So what is the expected value? This is 0 plus what is the expected value of stochastic integral? Who remembers the properties? It was
martingale.
Yeah, it's a martingale, and so expected value of this martingale, it's its starting value, and the starting value is integral from 0 to 2. Yeah. Okay, we have some new properties plus, and for ordinary old friend Riemann integral, we have just expected value of 6w squared du. Okay, let's continue. So who remembers what is expected value of Brownian motion squared?
C?
Yes.
Yeah, we know that expected value of wu squared is just u, because wu has normal distribution with mean 0 and variance u. Yeah, it's just variance of wu. Yeah? So I may continue my calculations. 6u dwu, and what is the value of this integral?
No, it's 3t squared.
So it will be 6t squared over 2, and it will be 3t squared. So for example, we have calculated expected value of w power 4 without any integrals. Normally we would, without stochastic calculus, you would normally say that expected value of wt squared is the integral from minus infinity to plus infinity, some w power 4 times density function times dw, and this density function would be 1 over square root of 2 pi u, t times exponent of minus 1 over 2 w squared over t, something like that. So the old way, was to calculate integral, but we have a new way. Yeah, so Ito's lemma is useful. We can calculate some variances, some expected values using it. So that is the goal of my example, that using Ito's lemma, we have calculated some expected value easily. Okay? Yeah?
Yeah.
Yes.
Okay, let's go on.
Yeah.
Too much noise, I cannot hear the message. So I hear the noise, but if you like, could you tell it again? Sorry, I can't hear you. Okay, let's continue. Let's consider some more example. Let's say that yt is t squared times wt squared. So, or maybe, yeah. So in this case, dyt squared is 2t times wt squared dt plus t squared times 2wt times dwt plus correction term 1 over 2 t squared times 2 times, we can just write dt because it was dwt squared. Yeah, in this case, dyt is 2t wt squared plus t squared times dt plus 2t squared wt dwt. This is a nonsense by itself, but we can recover full meaning that yt is y0 plus integral from 0 to t to u wu squared plus u squared du plus integral from 0 to t to u squared wu dwu. Okay? Yeah?
Yes.
Yes.
Okay, let's generalize Ito's lemma to more complex cases. So first, we continue with Ito's lemma. We just generalize it to more interesting cases. So Ito's lemma plus. So if xt is a Ito's process, and yt is a function of t and xt, we should also have f prime t, f prime prime 2x, 2x, f prime x continuous. Then dyt equals to f prime with respect to t dt plus f prime x with dx plus 1 over 2 f prime prime with respect to x dxt squared, where dxt squared is calculated. It has no meaning, but we can do shorthand calculations, and something true will correspond to shorthand calculations in a real world, where dxt squared is calculating according to rules, to the following rules, three rules. dt times dt is 0, dt times dwt is 0, dwt squared is dt. Okay, let's apply this more general Ito's lemma to an example.
And Boris, what XC is here? Before it was Wiener process WT.
Now it's Ito process.
XT is in, oh, sorry, I see. Yeah, sorry.
XT is Ito process is a sum of two integrals. So many processes may be represented as a sum of two integrals. So, for example, Brownian motion itself is a sum of two integrals, yeah. But that's a very simple. So WT is integral from 0 to t 1 times dwu plus integral from 0 to t 0 du. So Brownian motion itself, so it's really a generalization because in previous case, y was a function of t and Brownian motion, and now y is a function of t and x, which is a sum of two arbitrary integrals, one Ito integral and second Riemann integral. Okay.
Thank you. Yeah.
Borisovich, I have a question.
Yeah.
Can we state that YT is Ito's process as well?
Yes, here is the proof. YT is an Ito process.
Not WT, YT.
Ah, YT, yes. Sorry, yeah. And this is the proof. So basically, Ito's lemma is all about that. So yes, YT will be. So let's check an example. You will see that the lemma is exactly about this. Okay, so let's say that. Let's consider something from Black-Scholes model as an example. In Black-Scholes model, the share price is governed by the following equation. So it's in shorthand notation, yeah? Mu st dt plus sigma st dwt. So it's a shorthand notation. And my question is, let's consider discounted share price. So let's consider YT, that is YT, that is something like exponent of minus RT times, let's say something that is more interesting, times something like ST squared, yeah? It's a discounted squared price, and discounted squared price. And let's calculate DYT. Okay, let's start. First, I take derivative with respect to t. What is the derivative with respect to t?
Minus r, exponent to the power minus RT.
Yeah, minus r, exponent minus RT st squared times dt. This is like f prime with respect to t. Now, f prime with respect to s, it will be exponent minus RT2st dst plus one more term. It is 1/2 Now I take f prime prime with respect to s with respect to s, and it will be exponent of minus RT2 times dst squared. And now I simplify the answer to see that it's really it is process. So now that's correct. So now I just simplify because I have an expression for ds. I have an expression of ds, and I will plug this expression for ds, and I will simplify according to these three rules. These rules say that dt times anything is 0, dwt times dwt is dt. I will even copy these rules. dt times dt times dwt is 0, but dwt times dwt is dt. Okay, let's simplify. dyt is,
Are we allowed to use these formulas without explanation?
yes,
Thank you.
it's Ito's lemma. Yeah, we will not prove it. If you'd like a honest proof, then Baldi, we have discussed with my friend Dima Barzych, we have discussed that there are some gaps in the proof in Zastavnyak, but it's almost honest proof. I think I don't remember the proof in Baldi. So if you'd like a rigorous proof, then I think Baldi or Steel will be okay, or Shri. I don't remember the proof in Steel. No, in Steel it's okay. In Shri, I don't remember whether the proof is honest or with some gaps. So honest proof, you go to Baldi or Steel. Zastavnyak has almost a good proof, but some minor gaps. Okay, so I just simplify exponent minus r minus rt st squared dt plus exponent minus rt2 st. What is dst? It was mu st dt plus sigma st dwt plus exponent minus rt times no 2 disappears. What is dst? Mu st dt plus sigma st dwt squared. So now I simplify everything. Or maybe, so let's first simplify this stuff. Because I have some Ito's rule that dt times dt is 0, dt times dwt is 0. So the only thing that will remain there is sigma squared st squared dwt squared. Yeah?
Yes.
Yes.
Okay. Any questions?
No, that's clear.
Now let's finally write everything in one line and finalize the answer. dyt is just minus rtst squared. Or maybe even I will get rid of exponent minus rtst squared. Will be minus rdt plus 2 mu dt plus 2 sigma dwt, and from the last term I get plus sigma squared dt. And finally, I get dyt is, I don't like to turn the page, exponent minus rtst squared. And here I will have 2 mu plus 2 plus sigma squared minus r times dt plus 2 sigma dwt. And I see that my y is in its process because it's just a sum of something times dt plus something times dwt. Okay?
Okay.
Professor,
So basically we have proven that yt is in its
can
process.
you take this down again? Can you take it from dt? Can you take the last expression down? The last expression down. Not too clear.
I don't understand what you mean. So let me write some numbers. Okay, this is the first one.
Yes.
Second one. So
that is e exponent minus 2t.
So which line is not clear?
Okay, that is line 5. Line 5.
It just I have collected all the terms in line 4.
Yeah, that wasn't too clear.
So just a collection of all terms. So you have this is 2 mu, this is 2 mu, 2 sigma squared, this is sigma squared. So just collection of all the terms.
Oh, okay. Thank you, Professor. Thank you. Thank you. It's clear. Thank you.
Just to see that there are only something times dt plus something times dwt. No other terms remain. Okay. So let's move on. So small theorem provided so if expected value of 0 to t a x integral from 0 to t expected value xu squared du is not divergent, and then xt is a martingale if and only if and only if dxt is something times dwt. No bt times dt is present. So for example, if I see a process like dyt is wt squared times dwt, so I conclude that yt is a martingale. If I see that dyt is twt times dt plus wt cube dwt, I immediately conclude that yt is not a martingale. Okay?
Clear.
Clear.
So we have, so basically it's just an extension of a previous property of Wiener integral, of Ito's integral. So the stochastic integral is a martingale, but any non-trivial Riemann integral is not a martingale. Okay,
So
and
I'm sorry, you mean not a martingale? Because it's
Yeah.
written it's a
once
martingale
again, so if
in
you
the
mean
last row.
stochastic integral is not, it's my mistake. It's not
It's not a martingale.
Yeah.
Excuse me, Professor.
Is it is process or not? The
It's
last
not clear
line.
why the last line isn't a martingale for me.
Because it contains dt. So what does the theorem say? If you have only dwt, then it's a martingale. If you have dt term, then it's not a martingale.
So we do not have to check this integral of the expectation, that it is finite.
I don't understand your question. It depends on the question. So we do not need to check. It depends on what's your goal. If you would like to go into the cinema, no, you don't check. You don't need to introduce a stochastic integral at all. So it depends on the task. If the task is calculate expected value of something, you need to calculate expected value. If you need to check whether something a martingale, but the time is discrete. Oops, the time is discrete. There are no stochastic. So you have no. You have some analog of Ito's lemma in discrete time, but it's messy. Basically like this. So it depends on the goal.
So I mean that by the theorem, if the integral of the expected value of x is finite, then we can tell that xt is a martingale if and only if the dxt equal to at multiplied by dyt.
Yeah. You basically read the theorem.
Yes, but here we do not prove it. How can we understand that the integral is finite?
I have in the beginning I've told you that we will not check some technical assumptions. It's to in this particular case that I have written, you indeed can check. Why not? Just take expected value or square it. So in this particular case, you can check, but we will not check. I've told you in the beginning that our course is not rigorous. We will just use the theorem without always checking all assumptions. So the assumption that this integral of expected value of squared process is not divergent, we will not check this.
So is the last row an ITAS process? Then?
Sorry?
Is the last row an ITAS process?
YT is ITA process in both cases.
Yeah. In both. Okay. Thank you.
Because what is ITA process? ITA process is something like if you have dyt.
Yeah, we told that the martingale is an ITAS process.
dt plus, I don't know, elephant, dwt, then yt is ITA process. ITA process is just a sum of two integrals. Yeah, this is shorthand notation, full form. It means okay. So ITA's process is just a sum of two integrals. If there is only one term, that one. If there are no hedgehog term, then the process is a martingale.
Is a martingale. Okay, thank you.
Not all ITA's processes are martingales. All stochastic integrals, provided this technical condition, are martingales. But roughly, if I'm working in this under these assumptions, then all stochastic integrals are martingales, but not all ITA's processes are martingales. Okay. And finally, the next thing in a more general form. So with ITA's lemma with two processes. So if you have yt is a function of t, I don't know, xt and zt. Xt and zt are ITA's processes. All but there are a lot of derivatives. Derivatives are continuous. Then dyt. I just like take second order Taylor expansion, that it will be f prime to t dt plus f prime to x dx plus f prime to z dz plus correction term 1/2 f prime prime x x dx squared plus f prime prime z z dz squared plus 2 f prime prime xz dx dz, where the expression is calculated. Expression is calculated according simple rules. Is calculated using dt times dt is 0, dt times dwt is 0, dwt times dwt is dt. And basically, Ito's lemma allows us to calculate various links for Ito's processes. Basically, it's the main use. And using these links, sometimes we can simplify expected value, sometimes we can simplify variance, and so on. So that's all for today. See you next time.
But it's
If you have any
basically,
questions,
may I ask a question, please?
Yeah.
So could you return back to Ito's lemma plus? Do I understand it right that we proved actually that if xt is a Ito's process, right? And yt is a function of t and xt, then yt is also Ito's process. That's what we proved.
We have, but if we believe in Ito's lemma, then yes. But the hardest task is to prove Ito's lemma. So, so if you believe in Ito's lemma, then yes, we have proven that. But I don't think that counts as a honest proof, because, but yes, in that sense, you are right.
What we proved then here, if we don't believe in Ito's lemma, what was the purpose of this exercise?
Just to show you, just to practice,
okay.
Just to understand what does it mean, what does it mean use, what does it mean calculate using these rules? Yeah.
Okay.
So what do I mean by this expression? Because it's not so the danger here is that what is the problem? Why it's calculated and why it's not rigorous calculation? Because this object dyt has no meaning. It's not a random variable. You can calculate its expected value, its variance. It has no distribution function. The dst has no meaning. Dyt has no meaning. So basically, every equation we have written has a corresponding full form, and the truth is there. Yeah. So true mathematical expressions are there, and this is just shorthand. So by this expression, I really mean st is s0 plus the sum of two integrals. Yeah. By that expression, I really mean that yt is the sum of two integrals. Okay.
Yeah. Okay. So thank you.
My main point was that we have a little bit dangerous from mathematical viewpoint, a way it's a little bit dangerous because we are working with non-existent objects. So it's like small o. You cannot draw the plot of small o. You can say, oh yeah, we are in. Let's draw the plot of small o function. Because small o, it's not a particular function. Yeah, it's just an agreement that makes calculation of limits easier. And Ito's lemma is also like an agreement that makes working with Ito's processes easier. But this DST has no meaning by itself. That must point to be a little bit to avoid writing something like yt is dst. This is nonsense, because yt is a random process. I can calculate its variance, its expected value, and dst is just a shorthand notation. So my main point is just be attentive. We are working with non-existent objects, okay?
So may I ask you a question about it, Lemma? Yeah. So is it like about that if xt is an ethos process and yt is function of t and xt, is this about that y of t or yt would be an ethos process, or is it about the decomposition of the, okay. And what is it?
And it states precisely how to obtain the corresponding expression for yt.
And what is what is the meaning of ethos process? I don't really understand what is itself.
So imagine roughly any random but continuous process, and a very large class of continuous random processes in continuous time that are, they can be represented as a sum of two integrals. So that's a useful representation of large class of processes.
Okay, so it's about representation.
Yeah, because for example, obviously there are so imagine like a case in standard calculus. Obviously there are non-differentiable functions. Yeah, there are something like absolute value of x. It has a I don't know, kink, or how it's called, kink below. Yeah, it can represent absolute value of x as an integral. Yeah, it's not possible because it's not differentiable. Yeah, but a lot of functions can be represented using one integral if we speak about deterministic case. Yeah, a lot of functions can be represented as one integral. Yeah.
Okay.
So for example, x squared can be represented as an integral. Yeah, no problem. X cubed, no problem. Cosine of x, yeah, no problem. Cosine of sine of x squared as an integral. Yeah, no problem. You take the derivative and you say, oh, my original function was the integral of my derivative. Yeah. So a lot of functions can be represented as one integral in deterministic case. And this lemma says that in stochastic case, a large class of process, why ethos processes are useful, that a large class of processes, a large class of models can be represented as a sum of two integrals. Okay, not all. There are there are many bad processes like absolute value function, but it's just a large class of process that is useful for modeling purposes.
Okay, thank you.
Can you please, Boris Borisovich?
Yeah.
Can you please say, so any martingale is an ethos process, yes?
No.
Any ethos process is a martingale.
No. My statement is different. My statement is the following. Consider this is ethos processes. So this is a class of ethos processes. And there is a subclass. So let's consider assumption. So no, that's a bad thing. So what I assume, so imagine there are a lot of some assumptions. So we have assumed that this assumption holds. Yeah, we have assumed that this integral is convergent. Yeah, as an assumption. So we have a separated class of processes. Okay.
Yes, yes, yes.
Okay, then inside this class, so we are working inside this class. Outside this class, some monsters, there are martingales, there are good processes. So first I limit a very small, I have already excluded some bad processes, but they may be martingales, they may be eta processes. So I have I'm working with a subclass of eta processes, okay?
Okay.
So I'm not working with all ETAS processes. There are ETAS processes that are not martingales, that have no, so I have a subclass. Okay, so first, so when you say such general statements, you should be careful because I have not said so. I said if provided some, okay, first assumption. Okay, then let's consider ETAS processes that satisfy this assumption, okay? Then you have ETAS processes that is like this. It's I0 plus integral some AU dWu plus integral 0 BU dWu. So if there is this term with A, non-trivial, non-equal to 0, and it's not a martingale. If there are no such term, then then this process is a martingale, okay? So if it's not 0, then IT is not a martingale. So if IT is I0 plus from 0 to T BU dWu, then IT is a martingale.
Okay. And what is sigma?
Constant.
Sigma is just constant, yes?
In Black-Scholes model,
well,
yes.
You constantly write sigma is constant.
Where I constantly write sigma only here.
Sigma squared, ST squared.
So in Black-Scholes model, mu and sigma and r, mu, r, and sigma are constants.
Okay, thank you.
Boris Borisovich, may I have a question?
Yeah.
I have a question about examples 1 and 2, just after the ETAS lemma first.
Okay.
Could you tell how have you calculated this integral? You just used the answer we calculated in the previous class?
No. I have just moved it to the left-hand side.
Clear. Thank you. But on the next page, we will do just the same. I mean, with the example number 2.
Yeah, I'm not using any previous knowledge from last class, so I just use ETAS lemma. I show you that ETAS lemma can be used to, in the first example, I've used ETAS lemma to derive stochastic integral without taking limits. Example 2 shows how to calculate expected value of WT to the power 4.
Yeah, I got it. Thank you.
So I showed just 2 examples of use of ETAS lemma. So we may use it differently to obtain different things. Okay, so let's finish for today. Have a nice day. See you next time. You may ask always your questions in Telegram. So don't be shy. Okay, bye-bye.
Goodbye, thank you.
Thank you.
Bye.
Bye.
Thank you.